Hello everyone, and welcome to part 7 of our ANSYS Fluent tutorial series. I'm Mohammadreza Teimouri, a mechanical engineer, and in this video, we'll focus on importing and reviewing results in ANSYS Fluent, especially when working with solutions generated outside your current session, such as from a remote cluster or previous Fluent job. Let's walk through the steps to import an existing Fluent solution into Workbench. First, make sure to stop the current iterations and then close the existing Fluent session. Return to your Workbench project page. Drag a new Fluent system from the toolbox into the Workbench workspace, and rename it to something like imported_result to keep things organized. Now, in the Setup cell, B2, right-click and choose Import Fluent Case. Select the file. Workshop3 converged.cas.gz. Fluent will now launch. When prompted, make sure to enable double precision, then continue. Once the case is open, simply close the Fluent session again. Next, go to the Solution cell, B3, right-click and choose Import Final Data. Select the file. Workshop3 converged.gz. Finally, double-click the Solution cell, B3, to reopen Fluent and continue working with the imported results. Now that we've imported the case and data files, it's time to check the solution monitors to assess the status of convergence and simulation behavior. From the navigation pane, go to Monitors, then click Edit under Residuals, Statistics, and Force Monitors. In the Residual Monitors panel that appears, click on Plot to visualize the residuals from the imported solution. As you can see, the residuals are still quite high, even after 140 iterations. This suggests that the solution has not fully converged yet. Additionally, if you observe the surface monitors, such as lift or drag coefficients, you'll notice that they are still changing over time, indicating that the flow field hasn't reached a steady state. This is an important step. Always make sure to check both residual plots and physical monitors like forces or heat transfer to judge the true state of convergence. If the trends continue to oscillate or drift, you may need to continue the simulation or consider switching to a transient approach depending on the flow physics. Now let's talk a bit more deeply about why we check residuals, monitors, and fluxes after importing or running a simulation. While residuals are a primary indicator of convergence, they don't always give the full picture. Sometimes, especially in cases with complex physics, residuals may appear to plateau or even fluctuate, but that doesn't necessarily mean the solution is physically accurate or balanced. So we need to look at additional metrics, like flux reports, to ensure the conservation laws are satisfied. From the navigation pane, go to Reports Fluxes, and click Setup. In this panel, we can compute the mass flow balance across all domain boundaries, essentially verifying if the amount of mass entering and exiting the domain is equal. Select all the inlet, outlet, and other boundaries involved in the flow. Then click Compute. Now focus on the Net Results section. If you see a large mass imbalance, it means that the numerical solution violates mass conservation, which strongly suggests that the solution hasn't truly converged, even if the residuals seem low. This step is crucial because in fluid dynamics, conservation of mass and energy is fundamental. So if your net mass or net energy, heat flux, is not close to zero, the results of your simulation can't be considered reliable. You can also switch the report type to heat transfer and calculate net heat flux using the same process. This helps confirm whether energy conservation is maintained in thermal simulations. Once you're done, close the panel and use this insight to decide if you need further iterations, adjust boundary conditions, or possibly switch to a transient simulation. Now that we've reviewed the monitors, residuals, and fluxes, it's time to close the Fluent session and move toward more advanced post-processing. Go to the top menu and select File Close Fluent to properly shut down the session. Remember, ANSYS Fluent comes with basic built-in post-processing tools. These include options like plotting contours, vectors, streamlines, and generating surface or volume data, which are useful for a quick visual or numerical check of your results, even during the simulation process. However, for more advanced visualization, data extraction, and comparison tools, we use CFD-Post, a separate, dedicated post-processing application integrated within ANSYS Workbench. CFD-Post provides a wide range of powerful features, such as detailed contour and vector plotting, streamlines with control over seeding and animation, surface integrals and derived variables, custom expressions, calculators, and automation tools. So in the next part of this workshop, we'll begin working inside CFD-Post to explore and interpret our simulation results more thoroughly. This will allow us to generate professional quality visualizations, extract meaningful engineering data, and validate whether the simulated physics match our design expectations. Let's move on to CFD-Post and get started with advanced post-processing. Before we start exploring more advanced features in CFD-Post, let's quickly go over the proper way to add a results system to your Fluent setup in Workbench. From the toolbox on the left, drag a results system into your project schematic. Drop it directly onto the solution cell of the Fluent system. This will automatically link the Fluent solution data to CFD-Post, forming a connection between them and the Workbench environment. You'll now see a new results system appear, with its B2 cell connected to the Fluent solution cell. To launch CFD-Post, simply double-click on the results cell, B2. This will start the CFD-Post application and automatically load your Fluent results, including mesh, boundaries, and all available solution data. This method ensures that your post-processing environment is correctly synchronized with the Fluent results so that you can work efficiently with full access to all relevant fields and derived variables. Once CFD-Post is open, you're ready to start visualizing and extracting meaningful engineering insights from your simulation. Now, let's move forward and explore how to create professional plots and analysis visuals using CFD-Post. Now let's create a surface group to easily display results like temperature across all wall boundaries in our model. This is the most efficient way to visualize variables on multiple surfaces at once without creating separate plots for each wall. Step 1. Add a surface group. Go to the top menu and select Locations Surface Group. In the pop-up window, enter a name for this group, for example, all_walls or wall_temperature_group. Then click OK. Step 2. Define surface group details. Once the surface group is created, its details panel will appear in the lower left section of the screen. In this panel, locate the Locations field and click the button next to it. The location selector will open. Here, you'll see a list of all surfaces in your model. Hold down the Control key and click to select all wall boundaries that you want to include in this group. This can include outer walls, inner walls, inlets or outlets if applicable. Basically any surface where you want to visualize temperature or other field variables. Once you've selected all relevant surfaces, click OK in the location selector. That's it. You now have a surface group that combines multiple walls into one logical location. This group can now be used to plot contours of temperature, display heat flux vectors, perform area integrals, or export data for post-analysis. It's a powerful and time-saving method when working with complex geometries or large models. Now that we've created a surface group for the walls, let's go ahead and apply a contour plot to visualize the temperature distribution across those surfaces. Step 1. Apply temperature contour. In the outline tree, select the surface group you just created, for example, all_walls. Then go to the Color tab in the panel below. Click on Mode, and from the drop-down, select Variable. From the variable list, choose Temperature. Finally, click Apply. This will generate a colored contour map of the temperature field on the selected wall surfaces, helping you visually assess how heat is distributed throughout your geometry. Step 2. Customize the legend appearance. You can also modify the appearance of the legend to make it more readable or better suited for presentations. In the outline tree, locate the legend item usually listed under Annotations or Scene and double-click it. In the Details panel, you'll see various display options. To make the numerical display easier to interpret, change the precision format from scientific to fixed. You can also adjust the number of decimal places, font size, or even reposition the legend in the viewport. This not only improves the visual clarity of your results but also makes your plots presentation ready for reports, documentation, or discussions with your team. And that brings us to the end of this part of the tutorial. In this session, we learned how to import and link Fluent results into Workbench, launch CFD-Post for advanced post-processing, create a surface group to combine multiple wall surfaces, apply temperature contours to that group, and finally, customize the legend to improve the visual presentation of our results. These tools are essential for extracting meaningful insights from your CFD simulations. In the next part, we'll continue working inside CFD-Post and cover more advanced visualization and reporting features, including vector plots, streamlines, data exports, and more. So if you're finding these videos helpful, don't forget to subscribe to the channel and hit the notification bell, so you won't miss part 8. Thanks for watching, see you in the next one.